Hello, everyone. Thank you very much. Again, my name is Rickards, Vaught, and I'm here to talk more about electron temperatures and metallicities, but this time from aurora lines, and these are for H2 regions in nearby galaxies. Um, I think it's been stressed enough that metallicity can tell us many important things about the nature of galaxy evolution. They trace the galaxy's chemical enrichment history, as well as if you look at the variation of a galaxy's metallicity across its disk. The way metals are mixed can tell you about the efficiency of different processes like outflows, stellar feedback. And so, it's very important that understanding the galaxy's metallicity can provide essential insight into the several different kind of processes that drive galaxy evolution. Uh, so one way to measure a temperature or a metallicity or abundance is through the use of collisionally excited lines. You typically compare their intensity of their emission to a recombination line like H beta, and then compare that also to the ratio of their emissivity, which is basically all the ingredients, the quantum mechanics, transition probabilities, collisional rates, basically controls the strength of the line in different ionization conditions. Part of that recipe is the electron temperature. And one crucial difference between the recombination line and the collisionally excited line is their dependence on this electron temperature, with the collisionally excited line having an exponential dependence. What that exponential dependence means is that they're susceptible to temperature fluctuations. So they'll typically be biased towards the hottest gas. And so what this boils all down to is that to obtain an accurate abundance, you do have to have precise knowledge of the temperature. But we're just going to dig the hole deeper because there's kind of issues with measuring the temperature. One way to directly measure the temperature is through the use of auroral and nebular line ratios. Auroral lines are just transitions from upper excited states. So for oxygen 3, you have the strong nebular lines, which is 5007 and 4959. And the aurora line is the next level up, and for oxygen 3, that's 4363. Unfortunately, aurora lines are much, much fainter than their nebular counterparts. Just to see the auroral line for this H2 region from 2015 Berg paper, you have to create a separate inlet to observe it next to the nebular counterpart. So because of this discrepancy in their brightness, the discrepancy in brightness, past studies often pre-select the brightest H2 regions in nearby galaxies in order to maximize the number of aurora line detections in their studies. But what temperature do you use? Given that there's the stellar radiation field hardens as you get away from the ionization source, as well as different efficiencies in cooling from different ions, the H2 region ionization structure won't be uniform. And so often we can model an H2 region as consisting of 3 separate ionization zones. And each ionization zone can have its physical properties described from the emission of different ions that are largely dominant in that zone. So for example, the low ionization zone, you'll have a lot of O2, nitrogen 2, and sulfur 2. The intermediate ionization zone is sulfur 3, and then for the high ionization zone, that's going to be your oxygen 3. So it'd be really great to always be able to measure all 5 of these aurora line ratios. However, it does require a very large spectral range. You need between 3,600 angstroms and 10,000 angstroms in order to measure all 5 of these temperatures, with the O2 temperature requiring the biggest separation in wavelength. And because of this, there's empirical and modeled trends or temperature-temperature relationships that you can use to infer the temperature for one ion given a measurement of another one. So the goal of this study was to go out and measure all these temperatures using IFU spectroscopy and the power of 10-meter class telescopes to learn more about what may be driving variations in temperature and ultimately variations in abundances in H2 regions. So we obtained Keck KCWI observations for galaxies pulled from the FANGS-MUSE sample. The FANGS-MUSE survey consists of full data cubes, mosaics of galaxies within 20 megaparsecs. And I think it's about 90 galaxies at this point in the survey, with maybe 20 with MUSE coverage. Unfortunately, the KCWI field of view is less than the 1 by 1 arc-minute field of view of MUSE, so our job was a little bit harder. We had to observe several fields and step across the galaxy and then ultimately combine them into a giant, or to me, a giant galaxy mosaic. So this is just an example mosaic for NGC 1300. You see, again, we don't get the full overlapping coverage of MUSE, but we do get the most important part, all the star-forming regions. And what's great about using IFU is that not only are you getting the brightest H2 regions, but you're also getting the H2 regions that are basically within your sensitivity. And just to give you an example of the power of combining these two instruments, here's an example spectrum from an H2 region. Here we have the KCWI spectrum on top. Here we get the sulfur-2 auroral lines and the O3 auroral line. And then from the red side, we get nitrogen-2, sulfur-3, and oxygen-2. So we took those temperatures and first did a comparison of how do they relate to each other in temperature diagrams. Here we're showing only the low ionization zone temperatures, so oxygen-2, sulfur-2, and nitrogen-2. And we see that consistently nitrogen-2 has the least amount of scatter compared to sulfur-2 and oxygen-2, which is very apparent in this plot here where we see large scatter towards hotter temperatures. We believe this is possibly due to the presence of density inhomogeneities within H2 regions. The critical densities of the nebular lines of sulfur-2 and oxygen-2 are lower compared to nitrogen-2 and then the other ions. So what happens is that in high density gas, their emissivity is going to be reduced due to the strength of their emission is going to be reduced due to the effects of collisional de-excitation. So basically when you go measure an electron density using these nebular diagnostics, you're going to end up measuring the lowest density gas. So you'll end up underestimating the average density of the H2 region. And so one way to see how this would play out in terms of observations, we took a simple prediction from photoionization models that all the low ionization temperatures should agree with each other. And so we chose nitrogen-2 as the kind of foundation temperature, and then compared our measured auroral to nebular line ratios to those predicted using PINED for fixed electron density. And we can see that we can have many of our auroral lines reproduced by different values of density. So this basically turns into like a weight contest where you could have lower temperatures but higher electron densities, or you can measure lower electron densities and then end up with a higher temperature estimate for oxygen-2 and sulfur-2. Next, we compared nitrogen-2 to sulfur-3, which is the intermediate ionization zone, and we see that these have the lowest amount of scatter and at least tend to follow empirical and trends from photoionization models. A recent paper has suggested that nitrogen-2 is not affected by temperature fluctuations, but there's uncertainty on whether this would affect sulfur-3. So given the tight relationship between these two temperatures, really suggests that nitrogen-2 and sulfur-3 may be better tracing the average H2 region temperature. or the overall H2 region temperature. And then we started to compare our temperatures to different properties of H2 regions. So for example, ionization parameter. And we see that the largest differences between the high ionization zone and say like a low ionization zone temperature are in regions with low ionization parameter, which means that if you're in this corner here, your H2 region will likely be populated by oxygen in the first ionized state. So what you measure for oxygen that's been doubly ionized, you're actually only measuring like the hottest pockets of gas in the H2 region. So you're gonna get a biased temperature, which won't agree with sort of like the overall temperature that would be better traced by oxygen 2. This comparison with oxygen is similar to the results that were presented in Yates et al. 2020. They did not do this for sulfur, so this is a new result. But one issue that arises is that when you look at the different tracers of ionization parameter, this trend between sulfur 2 and sulfur 3 actually goes away. So this might be because sulfur 3 and sulfur 2 is tracing different ionization zones within the H2 region than O3 and O2. So these line ratios might change differently within the different ionization conditions compared to ionization parameter. Finally, I want to get to some really hot O3 temperatures that we measured. We compared these temperature differences to another property, the velocity dispersion for CO gas measured from ALMA data for these galaxies. And we see that the highest temperature differences these regions tend to have slightly higher or more enhanced CO velocity dispersion. And we think both of these high temperatures and the high dispersion might be explained by the presence of low velocity shocks. In a paper not so recent, they modeled different shock velocities at different metallicities, and they find that the O3 temperature can become much more enhanced relative to, say, sulfur 3 temperatures in the lowest or the highest metallicity regions. We did look for these shocks in both emission line ratios and in the kinematics in our spectra. These high O3 temperature regions seem to have emission line tracers that might suggest a secondary photoionization or secondary ionization source, but we weren't able to detect any kinematic evidence for low velocity shocks. So it's definitely a case of, is this plausible? We think so. And then finally, this is definitely more preliminary. We found that we can take our new temperature prescriptions and have fun in calculating abundances of different elements using different kind of temperature prescriptions. And we found that, for the sulfur abundance, if we replace the used temperature from sulfur 2 to nitrogen 2, we can actually get better agreement with recent trends predicted for the nebular line ratio with the abundance, but this is definitely still ongoing. So again, just closing, we measured aurora lines in H2 regions for nearby galaxies. We were able to measure all 5 temperatures from the different ionization zones. And then we compared those to themselves in different H2 region properties and find that sulfur 2 and oxygen 2 temperatures may be biased due to underestimated electron density, that nitrogen 2 and sulfur 3 temperatures seem to agree pretty well with models. So we're kind of going forward saying those are maybe the best temperature indicators, and that you can get high O3 temperatures possibly due to the presence of low velocity shocks. And then lastly, with KCRM, we don't have to play this game with merging KCWI and MUSE. We can just do it all at the same time. So that's going to be a huge leap for these types of studies and make them possibly more common. And then finally, I'm just going to leave you with the rest of the galaxy sample because they're great pictures. And yeah, that's it.